Okay, hello and welcome to this video lesson about energy in physical science. But first, why did the bike fall over? Might it be because it was too tired? Okay, what are we doing in this lesson? By the end of this lesson, my hope is that you'll be able to distinguish between potential and kinetic energy and to describe how energy is conserved, but its usefulness is reduced whenever it's transferred or transformed. Let's see what we're talking about. First of all, what is energy? So the science sense or the physics sense of energy is not that different from the idea you might already have in your head, right? So you might imagine like children with having lots of energy. Well, how do we know they have lots of energy? Usually because they're doing a lot. They're running around, they're making a lot of noise, they're talking really fast, they have a lot of energy, right? So more specifically in physics, we say it's the ability to do work. The ability to do work. Remember, work in physics is specifically applying a force over a distance. So energy is the ability to do that, and it can be used to move or to change matter. We talked about work in terms of the sense of maybe an object being pushed or something like that. That's not specifically all of energy or all of work. That's just the kind that we happen to focus on. So energy is the ability to do stuff, really, in the universe. And we categorize it in one of two big categories, either potential or kinetic. Potential or kinetic. So this is our first sort of split that we need to know about. Potential energy is energy that's stored somehow and can be used to do work. So it's not in use, but it's there and we could do it. And the classic example is you have a ball sitting on top of a hill. It's not doing anything, it's not using any energy at the moment, but give it a little nudge to go down the hill and all of a sudden it's going to do a lot because it had so much potential being up there. And then kinetic energy is energy that is actively being used to do work. So it's either potential, stored up, or kinetic. It's being used at the moment. All right, notice my take notes icon and make sure you're taking notes here. So here's an example. We got a skier. When he stands at the top of the hill, he has a lot of potential energy. But if he's not moving, he doesn't really have any kinetic energy. As he goes down, that's going to change. So by the time he gets to the bottom of the hill, he has a lot of kinetic energy because he's moving. He's moving very fast. That's what the little cartoony lines are for. He's moving fast, but he's now reached the bottom of the hill. He lost the potential because he's no longer at the top. He's lost the potential, and so sooner or later he is going simply to stop. So here are some types of potential energy. And you don't necessarily need to memorize these types, but you should write them down in your notes and be able to distinguish whether it's potential or kinetic energy. So here's 4 types. There are more than this, but these are 4 common types of potential energy, common ways that energy is stored. One is chemical potential energy, and that's energy that's actually held in the bonds within molecules. So examples would be food, right? Your food is made up of these molecules that in the process of digestion, you break the bonds and that releases energy that your body uses. Another good example of chemical potential energy is a battery. So a battery is where there is potential stored because certain ions are in certain places, creating a way for electrons to start flowing. A second major category of potential energy is nuclear energy. And that's related to the nucleus of the atom. So it's held in the strong and weak nuclear forces. And so when there are situations where the nucleus can be either broken apart or fused together with another nucleus, there's a tremendous amount of energy release. So fission is the common one that we see in our nuclear power plants and in the bombs that have been used. Fusion is the energy that powers the stars, and it's all related to the potential energy held in the nucleus of atoms. Gravitational is the one that we tend to focus on in this class, and that's basically the classic example of something is high up above a surface. So for example, in this picture, all of these skiers have a lot of gravitational potential energy. Because they're well above whatever is facing them down below, they have the potential to start moving really fast. They have the potential to do a lot of work. And then we have elastic potential energy, and that's essentially objects that have some kind of elasticity to them. So classically speaking, a rubber band is one. You can store energy by pulling or stretching a rubber band. And then you can see it turn into kinetic energy if you let it go and it goes flying and hits your friend, which you shouldn't do. Another example might be a spring, right? Certain springs, you can compress them and they'll hold energy. And when you let go, they'll go boing and release all of that energy. How about kinetic energy? Here are major types of kinetic energy we might come across. And the first is just mechanical kinetic energy, and that's when objects move. So remember, kinetic energy, this is energy that's being used. So mechanical is objects moving, like for example, this wheel, this bicycle wheel spinning has kinetic energy. Electrical is another type of kinetic energy that comes from the flow of electrons. So, that's your classical stuff that comes out of the wall or stuff that comes out of a battery. And that's, for example, what's keeping the TV on. This flow of electrons is passing energy from one place to another. It just happens to be in a form that we in our modern lives find very useful. There's heat energy, or it's also called thermal energy, and that's from the motion of particles. And you might remember this from other study of chemistry. We measure that average rate of motion of particles, and we call that temperature. And heat is a way of transferring energy, kinetic energy of particles from one thing to another. So for example, in this pot of water, you've got a lot of very hot water. The molecules are moving very fast in the water, and they move even faster as they evaporate and leave the water and become steam or water vapor. Radiant energy is electromagnetic energy that can be felt at a distance. You don't have to be touching the source of radiant energy to feel what it's doing. So a great example is sunlight, right? The sun is 93 million miles away, but the sun is still capable of making things feel very hot, right? For example, here's a mirage on a desert road. That's light coming from, light that we can see coming from 93 million miles away, hits this surface and is capable of making that surface very, very hot, which is actually what causes the mirage. It actually changes the density of the air above it. And then sound is another common type of kinetic energy. That's when an object is vibrating. And so commonly we see an object like a speaker vibrating, right? As the speaker vibrates in certain patterns, it makes what we can perceive as sound. And then we kind of have the reverse process happening with our ears, where our eardrums feel those vibrations, feel that energy, and then our brains tell us what that means. Okay, and now conservation of energy. Just like with matter, energy cannot be created or destroyed. If we look at a system where the system is completely closed off, we say that the energy doesn't just appear and disappear. It's just going to be converted from one form to another. And there's lots of conversions that can happen, but the energy is never going to go away. It's always there. That's why we call it conservation, meaning saved. We have conserved that energy. So here's an example of the conservation of energy and how it can be transformed. So you've got a hydropower dam. How does a hydropower dam work? So a dam is, generally speaking, a giant wall that you put in front of a river, and that builds up a lake behind it. So you've got this lake here, and they let water into the dam near the top of the dam, and then the water starts flowing down. So it has this gravitational potential energy that turns into kinetic energy in the flowing of the water. That in turn spins a turbine. So one kind of kinetic energy is transformed into another, where it's now spinning. And that spinning is used to spin some magnets inside of a generator, which generates electricity. So we've converted from gravitational potential energy to mechanical kinetic energy to now electrical kinetic energy that can be sent around via cables to your house or somewhere else that you might need that electricity. And in this video, here's just an example of how you can see energy transformations to do all types of work. This is an ad that Honda produced where they took the parts of a car apart and they basically had them come together in a contraption where all the different pieces do different things. And it's kind of a cascade of events. And this actually, it turns out to be one very complicated way to start a car driving. But you can get a sense of all the pieces that they arranged so that they could transform the energy over and over again. Oops. But, of course, you've probably heard the phrase, there's no such thing as a free lunch. So even though energy is conserved and it's always there, it's not always as useful. So that's something called the second law of thermodynamics. You will learn much more about thermodynamics in chemistry class, but the second law of thermodynamics says that when we change energy from one form to another, some of the useful energy is lost. So it doesn't mean the energy is lost, but it means that the useful energy is lost. We can't do as much with it. And usually it's lost to something like heat or sound. In other words, whenever we transfer or transform energy, it becomes less useful. So for example, if we transform the energy from our legs into riding a bicycle and turning those wheels, that's going to make us go, right? We're going to be able to do a lot of work with that. But the friction between the tires and the surface that you're riding on is going to essentially take some of that energy away as heat. And that's why you have to keep adding in more and more energy in terms of what your effort is from your body to keep the bike ride going. So what's the implications of that? Well, we see that when we see things like heat always goes from hot to cold, right? No one has ever been able to put a hot cup next to a cold cup and have the energy go from cold to hot. It always goes from hot to cold. Similarly, water or something else will always flow downhill until it reaches the lowest level. It will never go back the other way, right? In these two cups here, the water is never going to flow back uphill and go back in here. And the only way to do that is to add in new energy. And that's again because we lose the usefulness, right? The more physics sense is to say the order is getting less and less. We are getting less and less ordered as these things spontaneously happen. It's part of the nature of the universe. So it tells us we can convert energy from one form to another in many different ways, but we're going to lose the usefulness of some of that energy. And that is actually kind of extrapolated to the size of the entire universe. So what we say is the total amount of disorder in the universe. There's a fancy word for that I'm not going to go into now, but the amount of disorder in the universe is always increasing. In other words, there's always the same amount of energy, but the ability to use it is changing, right? And so we had lots of order way back when things were about at the Big Bang state, and we are becoming more and more disordered. Now, it's a very, very long process, and the universe is very, very big. So we don't really actively have to worry about the universe itself, but it does kind of give us an idea of what's happening to all of this extra energy that no longer is useful to us. Okay, I hope that gave you some initial thoughts about energy. Remember the difference between potential and kinetic energy, and that energy is the ability to do work. All right, thanks for watching. I'll catch you in the next video.